All right, so you know that GPS on your phone, right? It's amazing. I mean, it gets you to the nearest coffee shop, no problem. But what if you needed to do something a little more intense, like build a skyscraper, or map an entire coastline, or even land a drone on a target that's moving and get it right down to the millimeter? Yeah, for that, you're gonna need a whole different level of precision. And that's exactly what we're diving into today, the incredible tech that makes it all possible, DGPS.
Okay, so let's get right into it. To really get what DGPS is all about, we've got to first talk about the limits of the normal GPS we all use every single day. Look, it's a fantastic system, don't get me wrong. But when you're talking about professional stuff, surveying, construction, it's just, well, it's not nearly accurate enough.
And honestly, the difference we're talking about here it's just mind-boggling. Your phone's GPS, it's accurate to a few meters, which is great for finding your way around town. But in construction, a few meters of error, you could literally miss the foundation of a building. DGPS, though, it's in a whole different universe. We are talking millimeters. Think about that. That's the difference between being somewhere in the right area and being precisely on the head of a pin.
So what is this thing? Well, DGPS stands for Differential Global Positioning System, and I want you to focus on that first word, differential. That's the key to everything. This isn't just a bigger, better antenna. No way. It's a really clever enhancement to the whole system that uses two receivers, not just one, to basically hunt down and cancel out errors from the satellite signals.
Yeah, this whole two-receiver idea, that's the secret sauce right there. It's a totally brilliant way to solve the problem of satellite signal errors. And these errors happen for all sorts of reasons. I mean, everything from weird stuff happening in the atmosphere to tiny, tiny little clock errors on the satellites themselves.
Okay, picture this. When your GPS gets a single reading from one satellite, it doesn't just go, aha, you're right here, and give you a perfect little dot on the map. No, it's more like it draws a big circle and says, you're somewhere in here. Your actual spot is inside that circle, but the system isn't exactly sure where. But then your receiver starts getting readings from other satellites, so now you have more of these big circles. And you know, just like one of those Venn diagrams from school, the little spot where all of those circles overlap gets smaller and smaller. And that tiny intersection, that's a much better guess of where you're actually standing. And that, right there, is the magic of DGPS. By taking tons of readings, and here's the key part, using that second receiver to figure out the errors, the system just shrinks that zone of uncertainty down, 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 until it's just a tiny, super high confidence point. And that's how you go from a meter-wide blob to a millimeter-perfect location. So, okay, that's the theory. But how does this actually work out in the real world, on a job site? Well, this whole two-receiver solution isn't just an idea on a whiteboard. It's made up of two actual physical pieces of hardware that work together as a team. So, let's meet them. So, you've got two players on this team. First, you have the base. Think of it like the team's anchor. You set it up on a point where you know the exact coordinates and it doesn't move at all. Its one and only job is to sit there, listen to the satellite signals, and figure out, okay, what's the error right now? Then you have the rover. This is the explorer. It's the unit the surveyor carries around to measure all the new unknown points. And the whole time it's getting this constant stream of correction data from the base and applying it to its own measurements, like instantly. But wait, how does the base actually talk to the rover? Well, the most common way these days is called RTK, which stands for real-time kinematic, and real-time is the key word. It sends those corrections instantly, using a radio or a cell signal. That means the numbers the surveyor sees on their little screen are already corrected and millimeter accurate. The other way is called PPK. That's where you just collect all the raw data out in the field and then correct it later, back in the office, using some fancy software. All right, so we've got the theory down, right? The base, the rover, how they work together. Awesome. Now let's see what this actually looks like when a survey crew is out there, boots on the ground, on a real job site. And this is pretty much the standard toolkit. You can see the base station receiver right there, locked down on a tripod so it won't budge. Then you've got the rover. That's the unit on the pole that the surveyor is actually carrying around. And of course, the controller. That rugged-looking tablet, that's the brains of the whole operation. It's what connects the base and the rover and records all that super precise data. You know, looking at all this gear, the whole field procedure can seem kind of complex, right? All the buttons and settings, but really the basic workflow can be broken down into just a few simple, logical steps.
So how does it all come together? It's a pretty straightforward process, really.
Step 1, the surveyor sets up that base station over a point they already know the exact coordinates for. Step 2, they start a new project file on the controller. Step 3, the base locks on to all the satellites it can see and starts crunching the numbers to figure out those signal errors. Step 4, the rover links up with the base and starts getting those real-time corrections. And then, step 5, the fun part. The surveyor just walks around with the rover to all the new spots they need to measure, and with a push of a button, they record those incredibly accurate coordinates. And what do you get at the end of all that work? Well, you get a super clean set of data that looks a little something like this. Each point you measure gets its own ID number, a super precise 3D coordinate, that's your northing, easting, and elevation, and a little code to describe what it is. So, Healy could be the corner of a helipad, road could be the edge of a road. This right here, this is the raw, foundational data that engineers and architects use to create accurate maps and, well, build our world.
So if there's one thing to take away from all this, it's this. GPS is not just a better GPS. It's so much more than that. It's an active error correction system. It's a team. One part of the system is constantly figuring out the error in the satellite signal, and the other part is constantly removing that error in real time. That's what gives you a level of accuracy that a single receiver, no matter how good it is, could just never, ever get on its own.
I mean, this technology lets us measure and model our world with a level of detail that would have been straight-up science fiction just a couple of decades ago. It's what lets us build impossibly complex structures, monitor tiny, tiny shifts in the Earth's surface, and guide self-driving cars with pinpoint safety. And it really makes you wonder, right? Now that we actually can map our world down to the millimeter, what are we going to build next?